A Cartesian coordinate system is a coordinate frame with two orthogonal axes, called x and y. The x-axis is typically drawn pointing to the right, and the y-axis pointing upward. Their intersection is called the origin. Point P is represented by its x and y coordinates with respect to frame A, or equivalently, as a coordinate vector from the origin of the coordinate system to the point. Figure shows a red coordinate frame B that we wish to describe with respect to the blue frame A. The origin of B is translated by t sub x along the x-axis and by t sub y along the y-axis of A, and the frame is rotated counterclockwise by an angle theta. The coordinates of point P, when expressed in frame B, are x sub B and y sub B. The vector from the origin of frame A to point P is equal to the translation from A to B plus the vector from the origin of B to P. In other words, to reach point P from frame A's origin, we first move from A to B and then from B to P. Next, we resolve the vector BP into its components along the x and y axes. We denote these components as BP sub x and BP sub y. We introduce an auxiliary frame with the same origin as frame B and axes parallel to frame A. Using trigonometry, we decompose BP sub x and BP sub y into components along the auxiliary axes. These components are then expressed in frame A coordinates. Consider the vector BP sub x. Its magnitude is x sub b. From the right triangle, the adjacent side equals cosine theta times x sub b, and the opposite side equals sine theta times x sub b. Next, we examine BP sub y. It is perpendicular to BP sub x, and the auxiliary y-axis is perpendicular to its x-axis, so the angle involved is again theta. The magnitude is y sub b. When we project onto the auxiliary axes, we obtain minus sine theta times y sub b in the x direction, and cosine theta times y sub b in the y direction. Now we substitute everything back into the main equation. The vector BP is expressed as the sum of its two components, BP sub x and BP sub y. We factor out x sub b and y sub b. The term t superscript a subscript b is a translation vector. It gives the position of frame B's origin measured in frame A, and r superscript a subscript b is the rotation matrix for frame B relative to frame A. Now, we want to combine rotation and translation into a single matrix multiplication. To do that, we use homogeneous coordinates. We take the two-dimensional vector and add a 1 as a third component. This gives us the homogeneous form. This equation tells us how to move a point from one coordinate frame to another. We take the point expressed in frame B, apply a rotation to align orientations, then apply a translation to account for position differences. The matrix T superscript A subscript B is called a homogeneous transformation. The tilde over P indicates that the vector is written in homogeneous coordinates.